Good morning, everyone. Thank you for coming on Friday morning. And today I will be basically presenting the sort of the first part of how a technical feasibility study will be carried out, mainly on site selection, the technical survey, the basic layout of the microhydro plant, and the second part on hydrological study. Uh, as you will remember that the during my previous presentations, uh, I covered different aspects of hydropower design and planning and preparation. I also covered large, medium hydro, small, mini, and micro hydro. Uh, Today, in the technical exercise feasibility, I will focus a little bit more on the mini and micro hydro because this is the focus of our capacity building program. So the first part is, as I mentioned, the site selection of a mini hydro project. I'm considering mini hydro to be less than 1 megawatt or 1000 kilowatt. These could be isolated plants or uh, uh, within mini grids, or it can also be connected to the grid. So, but the focus is more on isolated and mini grids that is supplying power to a village, a settlement, or adjacent settlements. So it's a little bit on the smaller scale mini hydro projects and micro hydro projects. First of all, what would you need to do the site selection? Uh, uh, as you know, that the two important parameters that are important, that define a hydropower project is basically the head and the flow. Because if you know the head and if you know the flow, the design discharge, you can calculate the power, how much of kilowatt, how much of megawatt. So the flow is slightly not within your control. It depends on the river, on the catchment. Whereas the head is in your control. You can define where you want to put the powerhouse, where will be the intake, and where will be the forebay. Okay, so basically you use topographical maps that are available. Okay, and these topographical maps, I have seen a little bit large scale topographical maps for Mozambique because since I have not been able to, unfortunately, come to Mozambique to meet you all and to meet the agencies responsible to prepare these maps data. I have just mostly focused on the information available in past studies, reports, and some in the internet also. So this is one example of a topographical map. And as you know, this is for actually a case not in Mozambique, this is in Nepal, but I'm sure such maps are available in Mozambique also. And these maps, in the case of my country, is in the hilly region, we get a scale of 1:50,000. And in the plain areas, we get 1:25,000 topographical maps. This is the scale. So I assume, of course, in the internet, I just get maps of, I think these are of low resolution, 1 in million or 1 in 250,000. but the important thing is we should use the best topographical maps. And I understand that you would be having maps of 1:50,000 or even better resolution. Uh, so these are the contours. I mean, as you know, the closer the contours, the steeper are the slopes. The wider, that means it's more flat, because the difference of elevation across the terrain is slow. Okay, but so now basically there is a river here that flows. It's very difficult to see here, but anyway, this is the headworks. And now they have, what they have considered is they have considered a headrest pipe up to the forebay. And now the important head is from the forebay to the powerhouse. We need to find out the difference in elevation. The flow is on the river, okay? How much of flow we need to find out, and how much we want to divert in the pipe or the canal, we need to know. So basically, we need to do a site selection where there is a river with enough flow, discharge, cubic meter per, in terms of cubic meter. And as you know, the flow varies from month to month. You know, in the wet season, you have higher flows. In the dry season, you have low flows. So what that means is, if you design your project for a high flow, in some months in a year, you will not be able to generate at full capacity. If your plant is 585 kilowatt, but if your design flow is not available, like in the case of Majau, it's 4.5 cubic meter per second. So if 4.5 cubic meter per second is not available, then you cannot generate up to the capacity of 585 kilowatt. So you have to be careful on the flow, but the head will be more or less constant. The forebay is here, the powerhouse is here, the elevation difference is the head. And now the next portion you have to decide is, you have to basically, when you go for a site visit, especially for large hydros, site visit is done by a big team, a hydrologist, a geologist, a civil engineer, economist, social scientist, and other experts. Whereas in small, mini, and micro hydros, basically you can have a small team, civil engineer and some socio-economic background person, electrical engineer would be enough. And then, but we have to basically, with using the maps available and during the site visits, discussing with the communities, because sometimes the community, the farmers, the chiefs of the communities know about this river. So you ask them, when is the minimum flow, up to what level is the flow, then you try to do the discharge. And also you have to now decide which is the best place for the intake, the headworks, which is the best place for the settling basin, okay? And what is the canal or the pipe alignment? You want to take it here, or you want to go a little bit up? I mean, this you have to decide. So this is the thing. And the powerhouse, where you want to locate the powerhouse and where the tail race is. So these alternately, there may be 2 or 3 options to decide on this. And of course, the best is you have to locate the structures and components in a suitable area. No, I mean, in the like suppose you have some important land that you don't want to disturb, then maybe you should try to find an alternative that you don't use that land. Also, it has to be stable. No, if there is a, suppose you are building your canal here or a pipe here, if there is a landslide zone, the slope is unstable, then that will be a problem. So you should look at the components based on the land use and the ownership. Who owns the land also is important. I mean, if, of course, if it belongs to the farmers or the private owners, you have to then talk to them, and you have to compensate them for the loss of their land. Because if you use the land, if it's a public land, maybe you don't have to do that. Also, the now when you build the powerhouse, you have to make sure that this is protected from floods. No, if there is a flood, like in Majau, I think in 2015, you had a high rainfall and a flood, and it destroyed the powerhouse. So the powerhouse location should be above the flood level. And this flood level is depending on the size of the project. It should not just be above the normal annual flood, but it should also be above, let's say, floods that happen one in 25 years or 50 years, because this can happen to you during the lifetime of the project. Also, you have to make sure it's cost effective. So the alignment should be shortest, it should be short, because the pipe, the cost of the pipe, the canal is important. The construction materials that we'll use, it should also make sure there is locally available construction materials. Also, you should make sure the powerhouse is near the load center, wherever it is, because the distance will also influence the cost of the transmission. So these are basic fundamental concepts, ideas that you need to make sure you follow when you do the site selection. And now, as I said, the most important part is the head, because you have to make sure the head you calculate is correct. So based on the identified forebay, okay, based on the identified forebay and the powerhouse, and you can use the initially topographical maps, okay, to get when there is available, to get an indicative available head. Based on your topography, you get the contour of the forebay here, whatever elevation, the contour of the powerhouse, then the difference will be your head. But the topographical maps also have their limitations, because the scale, as I mentioned, it is 1:50,000 or more, or 25,000 or more. So you use survey equipment to measure the head. And normal survey equipment, very commonly used survey equipment, as level machines. So this is a level machine. You find basically the level, and using that, then based on the angle and the staff gauge, the height of this level, then you transfer this level, the elevation from one point to other, then you can get the head. Okay, and also you can use digital theodolites. Nowadays, theodolites and total stations, these are equipment which can be used, and it can basically, these theodolites and total stations nowadays are very advanced, and you can even map the contour map. So when you have enough points of measurements that you do, but you need a qualified surveyor to do that. Another equipment quite widely used in very simple small microhydro projects is what is known as the ABNI level. This is basically just measures the angle and the distance by using a tape or something. Then based on the angle and the distance, you calculate the head. I will just show you what that is done. And nowadays, you have global positioning systems, which are connected to satellites that are above our head in the sky continuously. So nowadays, these GPS, in fact, even our smartphones have started having these GPS. And based on this GPS, the GPS has X, Y, and Z. They have the elevation above mean sea level. It has the location, the latitude and the longitude in a global system. So you can find these X, Y, Z using GPS. But of course, using GPS to estimate the head will not be so accurate, because these GPS. Yes, please. Especially the handheld GPS are not so accurate. Okay, it's not enough to measure the head, but it can be used to locate key components and load centers. Okay, so this is just an example. I have actually at the end of my presentation, I have given you some references, and these references have these examples. And basically, the ABNI level measurement is basically you use the measurement and you use the tape. So what you do is you survey from a thing, and then you get a staff. Okay, what is the height of this? Using this, what is the height of this location from the staff, the point, and then you use the angle, and then using the formula for calculating the because once you know the angle, the head, then you can get the length, or once you know the length, you can get the head. So basically, these ABNI measurements, and its vertical distance is ground distance, okay, ground distance multiplied by sine of theta, and horizontal distance is ground distance multiplied by cos of uh, theta. Okay, so ground distance is from because there is the angle is there, based on that it is found. So basically what you do using this is you start from the forebay and move downhill, then based on station, like you make from one to another point, you get the vertical angle, you get the slope distance, then you get the horizontal distance. This is the calculated thing, and this is the vertical distance. And over here, you move from 1 to 2, 2 to 3, 3 to 4, and so on to 6. Then basically, you get the head. This is the head is 132.79. And you get the sloping distance also, which is used to estimate the, for example, the penstock length. Okay, the sloping distance would be the penstock length. So this is just a simple ABNI measurement, level measurement you use to get the head. Okay, and this is the head. Of course, over here you can use your total stations and other equipment, but use and levels. These are more sophisticated, but a simple way is to get the ABNI. But for big, large, medium hydro, you have to use proper survey equipment. Okay? This is the head that is done. The other thing, I actually already showed you this slide in my previous lectures. I just want to just tell you that we have to also find the load, okay? How much of demand there is, what is the benefit. So basically in our project in Nepal, for example, the criteria we use is per household wattage. How much of power they use is about 120 watt we estimate, and we want to make sure there is at least 10% of productive end uses, for either for agro processing, small scale industry, and other thing. And as I mentioned, we also prefer a multi-purpose scheme because there is more when you have a simultaneous drinking water, irrigation, then you can also use this water when there is more water in the river, and then you can use it for other purposes, or so you don't need to fully use that water. So similarly, as I showed you again, so when you do the site selection, when you try to find the capacity, we have to estimate the load of the micro hydro or the mini hydro project also. So the loads are basically, you have domestic load for lighting and maybe connecting to your mobiles, agro processing, bakery. If there is a sawmill, that sawmill operates in the evening. I mean, of course, there has to be demand for it, no? Because these sawmills may not operate 24 hours. It may not be a large city, a town. It may be a village. So you have different types of loads, and then you try to meet what is the peak load. Now, as I said earlier in the previous session, initially the load will be different. But once you have a mini micro hydro project in that settlement, the business load will expected to increase after 3 years. There may be a cold storage plant. There may be other small and medium enterprises, people, because once you have power, energy will lead to other economic activities. So this is an important part that we need to consider, because you may want to design it for whatever, 600 kilowatt now, considering your present demand. But after 3 years, that demand could increase. So you have a different economic sense. And other thing that I mentioned earlier was you need to make sure that the slopes, okay, or the main components, canals, powerhouse, forebay, are located in stable slopes, okay, where I mean there is no chance of a landslide or a rock fall or other activity or a slip uh, happening, soil erosion happening that will damage your components. So what are the features when you look at it? If you have a geologist, geotechnical person, you will be able to go with the hammer and get the exact details of the type of rocks you have. Sometimes for small mini hydro projects, you may have to use your also judgment when you decide it. So basically, thick vegetation covered, including trees, standing vertically, these are considered good slopes, I mean stable slopes. Straight, even slope profile. Rock surfaces covered with moss, lichen, and weathered skin. Okay, because there is some water that is on the top, so it's not so it's not fresh. It's been there for a while. Hard impermeable rock with no or few joints, closed it should be risk joints, well packed debris, well established trees and shrubs, no active gullies. There's no gullies there. Never. So, but you should never construct on a filled built up area where you use excavated material from other location to build up to raise the height of the thing. If you build that, the structures will be not stable. So it should also not be, it should be far away from landslide zones. Okay, now uh, the 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 reference material I shared by chat, I will just go to that material right now, and because there are some, I just will walk you through that material. It's an example of the case in Nepal, but I think it can be quite easily adapted to uh, uh, to the case in Mozambique. And this is a tested format in different countries with involvement with a lot of development partners, UNDP, ZIZ, and other ADB, World Bank, other people also have used this format. So it gives you a very good format, and it also lists all the issues, important issues that you should consider when you are planning or doing a feasibility study of a mini hydro projects. So I will just for a minute stop sharing and open that file, so that, because I think if I don't stop sharing and open that file, there will be some problem. So just to shift to that file, just give me a minute. Okay. Just give me a minute, please. Okay, so this is, can you, I think you can see my my screen, right? Carlos, you can see my screen.
Yes, we can see it. Yeah.
Yeah. Thank you so much. Okay.
Just let me advert my people that this is also sent on the chat. You can download it. Colegas, aquilo que estamos a ver agora a ser projetado pelo Divas, ele enviou há pouco tempo, no início da aula. Podem apanhar esse documento no chat e fazer o download. Alguns colegas já fizeram isso. Já fizeram o download. Okay.
Thank you.
We can proceed with this.
Yeah, this is the format to use when you are, let me just get the, this is the format you can use to, when you do a feasibility study, what type of data, when you do a site visit, what type of data you will need. Okay. And this is based on, as I mentioned, this is an example of, we have what is known as the Alternative Energy Promotion Center. You might be having, I'm a little bit not fully familiar with the institutional setup in Mozambique, but I understand you have specific government public agencies that looks after mini hydro projects implementation and other things. Okay, so in this format what we use basically is, okay, we just go to the, of course these are the different, and we, so please don't mind that there are certain like terminology used in my country which may not be fully applicable in your in Mozambique. So basically you get the general names of the settlement, the coordinate X, Y, Z, latitude, longitude. You can use GPS so that you can locate in the map later. Okay, so this is, and who are the people in the team who are were involved in this study, and what were, who were the people who were interviewed. Okay, and so this is in the feasibility. We are assuming there was a pre-feasibility level, a more preliminary level of study already done. Okay, so there is a slight difference between pre, but in some cases there may not be a pre-feasibility study done. You may just have done a desk study, and you find that this project is a potential project. So you are now going for a pre-feasibility. Now, first of all, we need to make sure, okay, this is based on the the policy, the methodology used in Nepal. So, but as I mentioned, this is valid. So what we want to make sure is, we want to make sure that we use the best available technology. Okay. So is hydropower potential available there? In some cases, you may have, you may not have enough hydropower potential, because for hydropower, you need the flow and you need the head. So, and what we try to do is, what is the flow available 11 months in a year? Because we are considering micro hydro, that some may have less than 1 cubic meter. And as you know, LPS is liter per second. So 1,000 liter per second is 1 cubic meter per second. So, and we also talk about Q40. Q40 means flow that is 40% dependable. That means that 40% of the time, the flow is more than, at least 40% of the time, there is enough that that flow, there is more than that flow that you are considering. So, and what is the available head? So you try to do that. Then you also look at, is there a wind energy potential there? No? And what would be the unit cost and other things? Because you need, for wind, you may need a farm. You may need to buy the type of land, public, private, and others. So this is also, I mean, considered in the uh, in the study. Sorry, I just moved back. Sorry, let me do it from right. Okay, and okay, and then we also look at, is there a solar energy potential? What is the irradiation kilowatt hour per meter square available? And I think our Paul, our Dr. Paul, Professor Paul, he has already provided, I think I was quite impressed with the materials that he has provided. I mean, you are, I think the participants are able to get this information. But of course, you need for land, for solar panels and other things. But I will not go into the details because this has been covered by Professor Paul. And similarly, is there biomass potential there, gasifier? This has been covered by Mr. Bart. So I mean, you like this, I will discuss. So because this is an alternate energy promotion, so we're looking at renewable energy sources. We're not just looking at hydropower, we're looking at wind, solar, and biogas. Okay. So what is the best technology available? So you should try to find why we are selecting a hydropower project instead of a solar project, or why solar. But now this is based in hydro, so we are a little bit more focused in hydro. So we have to justify why we want to build this hydropower here. I mean, as being a hydropower engineer, I know the thing, but nowadays, as the other sources of energy are also getting very cheap and attractive. Okay? So the other thing that we try to then fix is we want to know how many, is there a road access in my country, especially in the hilly areas, the roads, because our slope, our roads are not very, especially in the hills. I mean, you have to walk. You cannot have a motorable road. Maybe in Mozambique, the situation may not be different. So if can you go to the site? In some countries, there are roads all over the country, but because my country is a little bit more very steep and a lot of many rivers and very mountainous. So this is the thing. So we need to get the site information also. Then we look at the technical information that we want. Okay, what is the source of the stream, the river? Where is the intake location? What is the elevation? No? Using GPS and other things. So we want to know what is the headdress, open canal, and what is the, I mean, you want to now, because you using these survey equipment, you have to now locate the alignment of the headdress, you have to locate the gravel trap, you have to locate the settling basin, uh, then forebay, penstock, and the powerhouse, and all get the information about the approximate length and other things based on the survey you do. Then, of course, you need to also make sure that your transmission and distribution lines are there. Okay, I mean estimates for that one. So similarly, you have to, on hydrology, you have to okay, now you have to measure what is the flow over there. No, you could use, what was the method used to measure the flow? Is there data that was done? So this is, and what are the upstream water uses? No, you have to make sure above your river, if people are using water, what are the chance for the uh, 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 for water diversion that will disturb your project? So you have to make sure that is there. What are the downstream water requirements? Maybe just below the intake, there are other water requirements. You have to make sure that these downstream water use is also not disturbed. What are the irrigation practices there? Is there seasonal, year-round, rotational? And then, because there is some like a little bit focused on Nepal, but there is a MIP method that we use in Nepal that is not important. So, but this, the hydrology has to be done. Also, we look at the multipurpose, as I said. Is there a potential for irrigation, drinking water, and other uses of water? Because sometimes when there is multipurpose uses, it helps the economics of that project also. And then you basically then you try to find the, based on the head and the water available, you try to find the, what is the maximum available power in a kilowatt. Okay, then you also draw a general layout over here. Okay, these are, so this is a very important thing. And so then the general layout of powerhouse, from the powerhouse, how will the transmission line, distribution line reach to individual house and individual load centers. Okay, so what are, then you try to find the villages, the settlements that needs to be electrified. What is the name of the settlement? How far is it from the powerhouse? How many houses are there? And how many houses will be connected? So based on that, you can get an estimate of the electricity use in that area. So electricity use from morning, evening, total hours, how much they would use. What is the per household, how much of demand will there be in terms of watts? I mean, they just use for lighting, maybe 10 bulbs. Nowadays, with fluorescent and other very low efficient lighting, it doesn't really um, demand a lot of electricity for just for lighting. So now, is there any settlements that is not from the power, which will not be excluded, because you have to make sure that there is equity in that thing. So what is the total domestic load? You basically find out. Okay. Similarly, then you find out the electricity market. Okay. What are the other electricity driven uses? As I mentioned, agro processing, small mills, cold storage, small enterprise or sawmill and what have you. So, and what is the, because, I showed you one diagram of the load curve, and what is the expected operating time, the schools, okay, the schools operate, the colleges and other things, how much of power they need, any business, then you do that. What are the mechanical driven end users, no? As I mentioned, the, 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 the rice mills and other thing. What are the, and after 3 years, what can be expected to happen to that? Okay. So you might say, you see, that there is, I don't know, there is some very important raw material available, agriculture products, then maybe you want to make a factory for that one. So that will need power. So that can, and this will depend on community participation. So then you will get the total system load. Okay. So based on the total system load, so you basically find the uh, total system load. Now over here, then you look at, okay, I call it NEA. Here you should EDM. So you should convert this NEF to EDM. Where is the nearest electrical grid? No, the uh, how far is the national grid? So nearest EDM distance from grid distance from here, because that is important, no? Because do you want to, will the grid come to your location? Because if your village settlement will be connected to the grid, then you should know beforehand. Then what are the other MHPs in the area? In different other villages, there are any medium hydro projects. Now, similarly, you have, what is the electricity income? So you want to now have some idea of the tariff. Okay, how many Mozambique currency per watt per month? Okay, so based on that, how much can you expect to get the income, the benefit, because you have to do a cost benefit analysis later on. Similarly, then you do an analysis of the agro processing market there. Okay, so list of mills, okay, whether they are using diesel, water powered within 5 kilometers of radius. So these agro processing mills will be using your energy before. Is it used for rice, maize, wheat, millet, oilseed, and other? I don't know, this may be different for Mozambique, but I think you can use the same procedure. Okay, so what will be the total income? You can get it from here. Then you also have to look at also what is the enabling environment? What is the, I mean, do the people, I mean, because for the project to be successful, you have to understand that you have to pay for electricity. Electricity cannot be free because you have to cost, unless there is government subsidy, you have to do that. What is the, there is operation maintenance. You need to, the community, the beneficiaries should understand this also. So what are the proposed management? Okay, you want to now make sure, will it be managed by FUNAI? Will it be given to the private sector? And other thing has to be decided by in the beginning. So because feasibility study doesn't mean just technical design, it also means the, the institutional, the policy, and the socioeconomic data. You also now need to collect the socioeconomic data. What are the key agriculture products there, okay, on this thing? So because this is important, that the people's willingness to pay. And also this is the social and ethnic, this is in Nepali. So I mean, sorry, because they do that. I'll try to bring this, revise this and send it to you in English. But basically, the ethnicity, social information of the communities should also be there. What are the education level? What are the current energy sources? Because you have to, nowadays you can also finance micro hydro projects using carbon offsetting. You can buy carbon credits, no? So for that, we are displacing other fossil fuel, greenhouse gas emitting sources. This is very important. What are the facilities, the post office, what, I mean, just to give you a socioeconomic concept. And what are the average household land holdings? How many, like in hectares or unit? Ropani is a unit in Nepal, so but it could be a different. So what are the government agencies, non-government agencies working in the area? No? Because this is very important. So you also need to make sure you get the rates of the local material. okay? Because this is important. What is the cost of sand, 1 cubic meter of sand, what will be the unit cost, and other things you have to collect when you do the thing. What are the transportation rates? What is the porter rate? What is the public transport rate? When you hire something, you need this also. Then also, like you want to get the financial background for how much equity share from the developer, how much of loan you want to need. So this information is also thing. And this 21 is the environmental and social aspects. You have to, as I mentioned, you have to follow the Mozambique government environmental social impact legislation. But but these are some of the important parameters that you should collect. Is there any protected area, government forest, lease land? Like, will the project affect any of these biodiversity? Will it pass through a national park? Is it in a wetland? Is it does it pass through a range with endangered species? So these are very important ideas you should get from the thing. Similarly, you should what are the impacts on soil erosion? What is the impacts on other? What is the and other on impact on biodiversity and conservation and the natural environment? So you have to basically do this, and also you have to now be able to say, will the impacts be significant? And also, like, also there is also human rights. Nowadays you have to make sure, will it disproportionately impact the poor, women and children and vulnerable groups? Is there, because sometimes these projects may have these type of unwanted impacts. What are the capacity building needs of the project? Are the people there, do they have the capacity to uh, operate this power plant? So all these things should be think. What are the impacts on labor and working conditions? What are the other things has to be there too? I think you can read this on community health and thing. On land acquisition, is there a need that the project needs to take some? Will it be constructed in private land, public land, government land, leasehold land? So you have to, do we need to, like, will it pass through a house, a village? So you want to relocate people. So this has to be also listed and estimated, identified thing. Other thing is, what are the pollution, environmental resource thing, pollution? Is there noise pollution you want to avoid? You want to avoid solid waste management. All these issues should also be listed. So based on that, then you have in Mozambique, you have your legislation which has ABC categories. This is based on Nepal, so you have to categorize from an environmental perspective. Then you should basically get a confirmation from a developer and surveyor who were the potential developer of this project. So this is a format which is, I think, very much applicable in any country in the world for mini and micro hydro projects. Okay, so I will stop now, and I think it's more or less time for a break, 10 or 15 minutes also. But before we stop, is there any question that you have on? Because I have been talking. Sorry, in the next session I will do some discussion within the group also. So, Dr. Carlos, can you
Yes.
see if there are any question now, or we take a break and we can come back after break and answer this question?
Colegas, há alguma pergunta? Alguém quer colocar alguma questão antes do intervalo? No, Divas, I don't think so.
Okay, so how long?
I think we can
take the break.
10 minutes. 10 minutes
Okay.
break.
Yeah, 10 minutes. And let me know when you are ready. Okay.
Exactly.
Thank you so much.
Yeah.
Okay. Yeah, welcome back. Yeah. Now, can you hear me?
Yes, we can hear you.
So thank you so much. I basically, in the reference format that I just went through, so we went into the socioeconomic aspects I explained. We also looked at the multi-purpose possibility of multi-purpose projects. So I would just like to spend about 5 minutes on what is the possibilities, what are the possibilities of having uh, in Mozambique mini hydro project, and the part of the canal or part of that water will be used for irrigation or water supply. Uh, do you have mini micro hydro projects with such hydropower projects with multi-purpose water uses in Mozambique? Dr. Carlos or anybody, do you have this is this possibility in Mozambique, for example?
It is a possibility, but I think my colleagues may give some concrete examples.
Yes, it will be nice if you can, yeah, because this is an important part when we do our planning. Then we should also look at other uses. Anybody?
Yes. Can you hear me?
Yes,
Yes, we
please.
can hear you, Stansi.
Yes, I think that Pequenos Libombo is one the example for this kind of possibility.
Right.
Yeah, we use to irrigation and we use water to another kind of users to Maputo, Boane, and Matola, and we produce the electricity.
Oh, that is
Thank you.
nice. What is the name of this project? Can you repeat it, please?
Uh, is Pequenos Libombos.
Yeah.
Okay, Dr. Carlos, maybe you can send me the name
I
later.
will.
Yeah.
Yeah, I will send you. Yeah.
Yeah, or put it in the chat box. Oh, that is nice. Yes, yes. Okay. And any other?
I just did it by WhatsApp. So later
Okay,
on
good,
you can see it.
good, good. Yeah, thank you so much. Thank you so much. Okay. So, okay, because you see, we also need to, this will mean that there will be some, uh, so when you have this, if you have multi-purpose benefits, you have benefits, also you have some costs, because sometimes, like for example, if you want to use the canal for irrigation also, then you have to pass this canal to cultivated land. So the alignment may be a little longer, okay, but you have additional benefit. Okay. Anyway, I think this is, I think we maybe I'll move on to the other topic. The other thing, nowadays with development partners, World Bank, IFC, African Development Bank, I'm sure they have prioritized on gender equity and social inclusion. Okay. So they want to make sure that single women, disadvantaged groups, widows, the poor, the conflict affected groups, marginalized groups, uh, they they are also not discriminated, number one. Also, there is a positive incentive in the terms of sensitivity. So now hydropower, big ones have it for sure. Even micro, mini, we need to have what is known as a gender action plan. When you want to do a development project, we want to have certain target on women. Let's say when you have labor, we want to also involve women, and the pay should be equal. Okay, at least 30% of the labor force should be women. And we want to make sure that there is no difference in the pay for equal work, equal pay. So also you want to sort of provide subsidies. No? So you need to find, these disadvantages social groups, which are also part of the project. So I would just now put another question. what do you think should be the JESI policy relevant to mini hydro projects in Mozambique? Is this relevant in Mozambique?
Colegas, qual é a vossa... Sim, sim.
I don't think Mozambique is an exception. Yes, indeed, we need very relevant JESI policies. Yeah. We still have a lot of gender inequality from top to down, you know. Interestingly, at the university level, we can see now a balanced participation in the classrooms. Targeting is important.
Yeah. Oh, thank you so much. I think it is. No, the reason I mentioned this is even mini hydro projects, because we really micro hydro projects, mini hydro projects that are really close with the communities. We should make sure that, and this is why hydropower can be a tool for gender equality, also for socioeconomic development, because it's not just getting electricity to your household, but also making sure that other social development indicators, objectives, targets are also monitored. Oh, thank you so much, Mr. Kamal. It was very nice to hear that. And because if you want to do I'm an engineer. I mean, I believe in cement, concrete, rods, electricity, and other things. But I think we all also are part of a society. So because the reason I say this is also hydropower projects also has a lot of negative adverse impacts. So unless we are able to show the positive impacts of hydropower projects, we will not be able to build hydropower projects anymore. So we have to make sure these gender targets, social targets are also met. Yeah, thank you so much. I think I'll move on now. Regarding the environment social safeguards, as I showed, there was a special section, item 21, on the reference format that I just presented before the break on the environmental social safeguards. We wanted to identify what are the disadvantaged groups, what is the need for a land acquisition policy. So environmental social safeguards are important part of any development project, including mini hydro projects. But of course, you have to follow the national legislation. And based on, this was, I showed you earlier, based on the ministerial decree of December 15, 2015, you have 4 categories of projects, A plus, A, B, and C. As I mentioned, I think mini hydro projects would probably be in B and C, but still you have to make sure that the environmental social issues are covered. I just do that. Okay, now I will move on to the hydrological analysis, because we looked at the head, we look at the demand, we look at the socioeconomic. Now, finally, we have to look at the discharge available, the Q available, okay? And of course, in my first lecture, Hydro 1B, I covered the different types of hydrological analysis data that you need to analyze. But today, I will just take some few examples. I will share 2 Excel sheets a little later, and which gives you example of some calculations. I will go through this now, but I will also encourage you to use those sheets using data from Mozambique, other data, to do the analysis also. Okay, now first thing is we need to measure the flow and the hydrology. Of course, when you have, most of these mini hydro projects will not have readily available data, okay? And flow is discharge, volume divided by time. In 1 second, how much of water will flow in the river, okay? And there are different techniques to measure the flow. One is the current meter, which is normally for large rivers and like even more than 200 liter per second, we measure the current meter. And also there are two other techniques. I mean, this bucket is just to give you an example, maybe small, you can use a bucket just to make a channel, then just collect the water in buckets. And how long does it take to fill one 20-liter bucket, something like that, then you can do that. Similarly, so if it takes 2 seconds, I mean, maybe a larger bucket, if it takes 2, 3, 5 seconds, then you know how much it costs, how much it takes time. Also, there is a method called conductivity. It's basically what is known as a salt dilution method. And this is basically used mostly in microhydro projects in Nepal. What they do here is they pour some salt and some distance away, they do the conductivity. When you pour some sodium chloride salt here, the conductivity of the water changes, and downstream they use what is known as a conductimeter and get the thing, and then you can see how much of water you can flow. I will not go into a detail, but this is available in the literature on this method. But I will just a little bit talk about the flow measurement using current meters. And basically, current meter, this is just an example, a small example of current meter. What it does is there is a current meter has sort of a rotor sort of a thing that when water flows here, it just rotates, okay? So based on the number of rotations in 1 minute, 2 minutes, you can estimate the velocity. There is a calibration curve that if this rotates, then you measure the velocity. And when you measure the velocity, the speed of the water that flows across the river, then you get the velocity. Then when you know the area, okay, the full area of water, so you know the discharge. So if the depth of, because obviously the cross section is deep in the middle, then it goes to the side. This is the water level. Now in hydro, and this is the, for small rivers, this is what is called the weighting method. This is the current meter they use. And then based on this speed of the velocity of the water, they get the area, they calculate the discharge. Okay, this is using a current meter. And what they do is they basically, because the velocity here, it varies from here. The maximum velocity is in the middle on the side because there is this frictional effect and other effects of the boundary of the river. And also the velocity is basically more or less highest at the top, although there is a slightly thing, but on the top, the velocity high. As you go down, the velocity is low. So normally you measure velocity for very deep river, you measure velocity at 0.2 and 0.8 depth, then get their average. But for shallow, you measure at the average velocity is at the 0.6 of the depth. But you divide the channel into 10 or 20 parts. There are certain norms to do that. So you get the depth here, you measure at 0.6 the speed, then you get the in this area, this is you get the velocity here, velocity here, velocity here by measuring at 0.6 depth. Then based on this area that of influence and the velocity, you add up, then you get the discharge. So this is the method of measuring discharge. And I'm sure this is done in Mozambique. I'm not familiar with the exact organization, but I will ask you a little later about that. Another simple method, if you want to, as you might have seen, if you go to a river, sometimes you can throw some floating object, some leaf or some ball of paper, and then you let the river float from here to there. Then you measure the distance of, let's say, 50 meter or 20 meter, and how long it takes to go, then you get the velocity at the top. But this is the surface velocity, and surface velocity is not the average velocity. Okay, so you measure here, so you measure across 3 to 5 locations, then get the velocity, then you get the, using some staff or something, you get the area, then you also made. But this is for rough estimate for the discharge. Okay, this is something that you use. And now based on the discharge, you basically, since I covered this in the first 1B session, I will not go into the detail, but the discharge varies from month to month, no? Because you have the minimum flow in some month, high flow in other months. When the rain comes, there is high flow. When there is no rain, all the groundwater base flow has low flow. Okay, so based on that, we calculate the average flow in each month. Okay, but one important thing of analysis, of hydrological analysis, is we have to calculate the flow duration curve. Okay, and this flow duration curve is basically a plot of discharge. On the left y-axis is the discharge, on the x-axis is the exceedance probability. So what we do here is we collect data. Normally it is on a daily basis for 365 days every year, and then for 20-30 years of data we collect. Then we try to find the what is known as the flow duration curve. And what we do, it's a very simple procedure. We collect the data, then what we do is we arrange the data in descending order. Okay, like you collect all the data, and sometimes you can use class intervals also. You can get the frequency of like in each interval, you divide into 10 interval, you can get the frequency and do it. But you can do it by just arranging. Nowadays in Excel, you can do that. So you can really get the percentage easily. So, and based on that, you get the percentage probability of flow being equal or exceeded. And M is the rank of that maximum flow or whatever the flow out of thousands of data. And N is the number of data points. You divide this N plus 1 times 100% is the formula to get the exceedance probability. And the reason you do, it should be M plus N. Probability is you are rank 1, then it is out of 1,000. If you are rank 1, that means 1 upon 1,000 is the probability that it will exceed that. But just to give the sample error, we use N plus 1. This is a simple formula. Okay, now I would just like to show you exercise using Excel. Okay, so let me just stop sharing and I will send you this Excel file in the chat box also, and you can download it now or later. Okay, but maybe later, but I will show it to you. But let me, okay, before I do that, I will shift. So let me just give me 1 minute. I will stop sharing the PowerPoint and then go to the Excel sheet. Yeah. I've also sent you the to everybody the Excel sheets for what we call the flow duration curve and the Gumbel. Okay. Okay. Now. Okay. Okay. Can you see my screen here?
Yes, we can.
Yeah. Okay. So what I have here is on the left, the first column A, I have the data from 1968, 60 to 1991. Okay. So if you go here, I have okay, from 1960. So we have data for January 20. It starts from January 2021, and this is the discharge cubic meter per second. Okay, and let me just see if let me just stop sharing for a while, and let's see if I can just shift my. Okay, no, it's all right. Let me not disturb. Okay, so now what I did here is I have this one is the data that I have for. Okay, this is the discharge data I have from 1960 to 1991, October 31st. Okay. Okay. So this is the discharge data. Now I want to basically find the flow duration curve of this data. And now to do the flow duration curve, I have to basically arrange this data, okay, this data into descending order. Okay, so what I have to do is I should copy this data, this data from the beginning to the end. I copy and I put it, okay, I just copy here and put it in this form, okay, like I put it. Now, after I copy this data in descending order, okay, I select this data. I think I assume that you are familiar with Excel. So what I do, I arrange this data in descending order by selecting this data and using the command data and sort. Okay, so I do here. Okay, it says continue the selection, expand, continue with the current selection. Then I do my data has no thing. I do from largest to smallest. Okay, so when I do that, I descend. Now, one thing I noticed was this data has some not available data also. So we actually, there are two ways. You can delete this data, because if there are some very few and scattered in different years, it is no problem to delete this data. Okay, but if it is very much, I mean, there are many, then you have to make sure that you find a way to estimate this data. Okay, and there are different ways to estimate this data. In my case, I just delete this data and I just shift all the cells to up. Okay, so what I did was the maximum discharge was uh, uh, 500. Okay, and let me just okay, the maximum discharge was 500 and the minimum is 0. Okay, this has 0 discharge also, and total number of data available is 11,169. So what we do according to the flow duration curve method, what we do is we arrange this data in descending order, then get the rank, okay, rank of this data. Like the highest data will get rank 1, the second highest will get 2, the lowest data will get accordingly the highest. Then the probability of this data is, so you do this also, and okay, this is part is done. Okay, this is actually automatic, okay, because I already put the ranking here. So I just, then this part is done. Then you calculate the probability of this data by okay, so the formula we use here is this rank divided by the maximum data plus 1. Okay, so actually the maximum data, actually I should I should put this here, this plus 1 is the, okay, so if I do this, okay, so I get the, so and the reason I put this 11170, this one is I put the maximum data is 11169, which is given by this equation. I could actually put 1 directly. So it is basically rank divided by the total number of data plus 1. Okay, so this is the equation we use. So based on that, now we draw what is known as this. If you see here, this flow duration. Okay. Okay. The actually this is the, I had already calculated the power duration. Actually, I should have been little. Actually, this one, maybe I'll send you a different thing. But what I will do here is I will just insert. Okay. So now what I have here is, just a moment. Sorry, I made. Okay. So basically, so I want to now, if I want to draw a flow duration, what I do here is I go to this chart and this formula, and I use the data, select data. I will send you this one, add data. So series name is FDC, flow duration curve. On x-axis is the this one, percentage. Sorry. Sorry, I made a mistake here. Let's do it again. Okay, this is. Yeah, so it is from the top to this column. Okay, and sorry, this is a mistake. Then I have to add on the y-axis is the is E. Yeah, so I think I made some mistake somewhere. Okay, and this one. Okay, I think there was some mistake in the formula I used. Just let me just do it again. Sorry, edit. This is series x-axis is. Yeah, okay. So basically this is the just to make it nice. I'll just put it. Okay, and okay, so this is the flow duration curve. Now, one thing we have to be careful is that there is a big difference of 500 and minimum is almost 0. So what I did was here was, then of course we can add this design. I will add the elements here. axis titles, primary horizontal, exceedance, probability percentage, and primary vertical discharge, cubic meter per second. Okay, so now the main problem is the difference is very high, so it looks very I mean the curve is a little bit looks funny. So but what I do is, instead of making the axis up to 600, I just will reduce it to up to 200, then it will, or even let's say 100. Okay, so based on this, okay, so this is the flow duration curve that you will get. Okay, and now you want to make sure, like if you want to design your project in, I mean 90% dependable, what is the flow, 60%, so like 40% dependable flow is 10 cubic meter per second. So in this case, I have actually already used here, I mean, using this formula, I have basically calculated the design, okay, if you go here, yeah. So what I have done is this design queue. Okay, maybe I'll just go to this better one. Okay. Oh, this computer is a little bit slow here. Okay, so okay, what I did was I estimated the design based on, from there I used a formula. I mean, you must be aware of such a formula also. What I used is I basically used what is known as a VLOOK. So from here, 95 dependable, percentage dependable. Now over here, I've used a power equation, okay? But 95% dependable, sorry, this is the power duration curve. 95% dependable flow is 1.9, and 40% dependable flow is about 9.8. Okay, so now the question becomes, if you design this project for 90%, if you design for this project for 90%, you will use 2.5 design discharge. Okay, if you use for 90%, you will use a design discharge of 2.5. If you use design discharge of 2.5, you get about 400 kilowatt if you consider 20-meter head. Okay, and you will get about 400. Now, if you use 5.5, is if you use 60% dependable flow, you will get almost 1 megawatt, about something like 916. Okay, if this one is, if you use 90% dependable flow, you will get maximum of 417. But when you have more flow, you will not get any power. So the power will be from here to here. Okay. So now if you design it for 5.5 cubic meter per second, you will get 916. If you design for 9.8 is at 40% dependable, 9.8, you will get 1.6 megawatt, or 1600 megawatt. But the problem is you will be getting only 40% of the time you will get full capacity. Other time you will get less. So basically, this flow duration curve that you make here will based on this, you can select your design discharge. Okay, so whether you want to do it, for 90% dependable, 90% of the time you get this energy power, 60% dependable, you get 60% of the time, 40% dependent. Now, if it is an isolated system, you don't have any other thing, then you have to design for very high exceedance probability over here. Then you are able to meet the power most of the time. Otherwise, there will be a problem. Okay, so basically, the method for for preparing your flow duration. Okay. Okay. So, okay. So now this basically the method of doing your flow duration curve is, this is the curve, I mean, that I showed. And then you basically arrange into descending order, then calculate the exceedance probability, then draw the flow duration curve. Then the exercise that I show, I would like you to practice, because there was maybe the model I have the data. I want you to practice. Then on Monday, when you have I have my next class on Monday this time. So you can ask me any questions you may have. Okay. And but if there is any question, I can take the question now too. Okay. Sorry. My computer is getting a little slow. Okay. I hope. Yeah. Dr. Carlos, you can hear me, right?
Oh, yes. Yes, we can hear you.
Okay. So is there any question right now? Or did I go too fast?
No, it's not exactly the question, but I don't know what's going on. I didn't receive the documents on chat.
Okay.
So if is it possible, can you share these by email, please?
Yes.
The first one in this Excel.
Yeah, I will share that. I will share that.
Thank you.
Share that after this lecture, okay? And please have a look at it. I will share you the Excel and the for both the flow duration and the new one that I'm going to cover now. Okay. So now actually we have about 5 or 10 minutes left. I want to just quickly go to the flood estimate also. Okay. The other important hydrological parameter that we need to estimate is the flood. Okay. And flood is defined as an unusually high stays in the river. Normally the level at which the river overflows its banks and inundates the adjoining areas. Okay. And there are different methods. There are what is known as a rational method. This is also known as the CIA method, because there's a coefficient multiplied by the intensity and the area. And this is based on empirical relations of many countries. And for rain dominated systems like in Mozambique, this can be thing. There are empirical based on many years of data of different stations. They do that. There are unit hydrograph techniques. And also we use what is known as the flood frequency studies. Today, I will briefly explain you the flood frequency method. Okay. And basically in flood frequency method also, we use a similar method like we use flow duration curve. We collect the annual series of maximum flood. So every year, what is the maximum flood? Okay, let's say 500 cubic meter per second in 1961, in 1962, 490 and other things. So we get the maximum annual series of maximum floods. Then we do the same thing. We arrange in descending order of magnitude. Then we calculate the exceedance probability using the same formula. And we call this T recurrence interval or return period or frequency of the flood is 1 upon P. For example, the highest, you have 30 years of data, the highest flood is recorded by once in 30 years. So we call it once in 30-year flood. So this is the basic. I will show you the example also, and I also send you by email. I will send it for somebody who did not receive. I will send it again. Okay. And basically the general equation we use is, I also presented this in the previous lecture, is if you want to find out what is the discharge flood, what happens 1 in 100 years. Let's say T is 100 years. What we do is we want to know what is the discharge that happens once in 100 years. We use this is a general equation. We use the equation called, this is the mean of all the discharge time series, that plus K is the frequency factor. And this frequency factor depends on the frequency distribution function, no? And like normal distribution, log normal distribution, Pearson, log Pearson, Gumbel, extreme value. These are statistical frequency distribution curves that are used to estimate these flood frequency analysis. Then we multiply that with the standard deviation of the data. So this is the general equation we use. And based on that, what we do, we get the different methods, frequency distribution functions using Gumbel, log Pearson, log normal, extreme. So this is the observe is ... And the other one is by different methods is based on this one. Okay. Now, what is the procedure to use the Gumbel method? First of all, this is the general method we use. And to get this K, we get this mean we can get from the data, standard deviation. This is standard deviation of sample size of N. Sigma and X bar, the thing we get from the data. Now we have to get the K value, the frequency value, which is expressed by an equation given by K is equal to YT minus Y dash N SN. Okay. And YT is basically, we get YT is the minus natural log multiplied by natural log T divided by T minus 1. If it is 100, then we say natural log times lateral log of 100 divided by 99. So this is YT. And this, and if you use the log to the base 10, we use this. And to get Y.
Hello, Davis.
Yes, please.
We cannot hear you.
Okay, can you hear me now?
Oh, yes, now we can hear you.
Sorry. So this is to get this K factor, we use this formula, and YT is based on the frequency return period T, which is given by this equation. In log base, this is the equation. For YN and SN, for Gumbel distribution, there are standard tables. I call it 7.3 and 7.4, which is based on the book I followed, which is given in this formula. So Y bar N, if you have 30 years of data, it has a value of 0.5362, and SN, if you have 30 years of data, has a value of 1.1124. This is based on the Gumbel distribution, the extreme value distribution. Okay, these are, I mean, you can go to the statistical books and get this information, but this is a very simple procedure. And based on that, what we do, the steps we follow is like we did for frequency flow duration curve. We collect all the data for discharge, n number of data, 13 years, 19 years, whatever data. Then we calculate the mean and the standard deviation. Then we calculate the YN and SN from using table 7.3, depending on the number of data. This 10 and 9 means if you have 31 year of data, then we use this value, 1.1159 for SN and 31, 5.53721 for this data. So this is 10, 11, 12, this way it is given. This is 19. If you have 100-year data, this is, and normally in developing countries, it's very difficult to get that data. Then based on this, using equation B, we calculate K. And once you get the value of K, for this value of K depends on different return period, we can get the XT value. So based on that, I will quickly show you an exercise. Okay, let me just go back. How do I go back? Okay, so I shared this file to you also. Okay, can you see? Yeah, can you see my Excel file? Maybe not. You are still seeing that. Okay, now it's low. Okay, now you can see my Excel file. Okay, so over here you have this data here. Okay, the data, I will just make this. This is just an example data. Okay. Okay, this example data from 1965 to, I have a very 1979, 19 years of data. I have the maximum discharge data here. Okay. Okay. And in 65 is 250. Like if you see here, in 65 it is 250. So this maximum data varies. So the maximum data, this flood occurred in 1969 here. Okay. So so you have this data, and based on this, the mean data X bar is this mean data is 342. This is the average. The standard deviation is 129, and this is based on the. Sorry, I should have the formula. Should have used the. Let me just use the formula because. Okay, the one that I sent you is. Okay. Okay, then this one is STD standard. I'm using this, sorry, let me just. Okay, this is the standard deviation. Sorry. Okay, the standard deviation is 129, and the number of how many years of data do you have? Count is okay. You have 15 years of data, and based on 15 years of data, and based on the SN curve. Okay, yeah. Sorry, this is. Yeah, okay. So based on this curve, you get this y bar n and SN bar, and based on this k value is based on this k value is based on yt minus y dash n over Sn. You get the k value. I think maybe I'm going a little fast, but you'll be able to get this value. And based on this, you have a 2-year return period would be 320, 2, 3, and 3-year return period is 390. So basically, now what you do is this is the peak. You get the descending order. You get the order by one of like the rank here, and based on this probability is based on 1 divided by 15 plus 1 divided by 16 is this one. So you get, this is the first data is 16 years, the second rank is called 8 years. So this blue one is the observed, and this red one is based on this Gumbel frequency curve. Okay, so basically this is the flood frequency analysis. So if you want to know what is the, for this data, what is the flood frequency for 1 in 100 year, it is about 800 something. For 1 is 1000 year, it is almost about 1200. The calculation is for 100 year is 860 and is given here. And this one I have actually shared with you, and maybe since we have a little bit, we've exceeded our time, I would like to stop here. I can take some quick questions, and sorry, I may have gone a little fast, but I want you to, as an exercise, I will send you an email as an exercise. Please use your data from Mozambique for any station, the frequency data and the flow duration, the flow data, and try to use the Excel that I have shared and the steps given in the presentation today, and come up and do your own frequency analysis, and we can discuss that. So please try to prepare Gumbel method for your data. Okay, this is the data I used is also for, I think, for Mozambique, some station I used, but I did not do further detailed analysis. So I would like you to try using the Excel sheet I shared, flow duration curve and flood frequency analysis. I can take some questions now. Any questions? Or if it is not clear, sorry if I was fast, let me know. I can explain, but otherwise I will see you on Monday and we can discuss further on this also. Yes, Dr. Carlos, can you?
Yeah. Well, thank you, Divas. Acho que todos percebemos, mais ou menos. Pretende-se que, com os exemplos dados e a partir dos ficheiros que serão enviados, que se faça um exercício até para ser apresentado e discutido na segunda-feira, usando dados nacionais, ou seja, dados de Moçambique. Portanto, voltaremos a ter aula do Divas na segunda-feira, às 9 horas, e nesse dia será discutida a solução, ou o caminho para a solução do exercício que está aqui a ser colocado. Alguma dúvida? No, I think we can finish, Divas.
Okay, thank you so much. And Dr. Carlos, can you share with Mr. Kamal and others the Funai 5 station, the hydro?
Okay. Yeah.
Okay. Yeah, you can share that.
Okay.
Yeah.
Okay. I will do that. Yeah.
If you did not receive the Excel, if you received the Excel, can you share with all? Because I send it by email. Okay. Because I think one gentleman said.
I got it. I got
it. Okay.
Yeah.
Okay.
Yeah.
Okay. Thank you so much.
But this you have sent to all, yeah?
Yes, I've sent to all. Yeah, all should get. If not,
so the participants might have it. So
okay. Good.
If someone, se alguém não tiver recebido, por favor, pode entrar em contato conosco, mas o Diva já enviou para todos 2 ficheiros. Né? E o ficheiro que foi apresentado para o exemplo que foi dado e para o cálculo de Gumbel, usando o método Gumbel. Se alguém não tiver recebido, por favor, põe-nos ao conhecimento e eu hei de fazer o forward, mas acaba de enviar para todos nós. Okay, if something happen, they will let us know. They will contact us.
Thank you so much. So, and I will do my next class on Monday. So see you on Monday.
Yeah, right. Yeah.
Bye-bye.
Okay, thank you very much, Divas.
Yeah, thank you so much.
Thanks so much and have a nice weekend. Huh?
Yeah, same to you. Same to you. I stopped
Thank you.
now. Okay.
Yeah.